This is the 20th video in our series on abstract algebra. And today we're going to continue our study of rings and ideals by looking at some really important types of ideals of commutative rings starting, but we'll look at ideals of other rings as well. So let's start with the following definition. So let's suppose that R is a commutative ring with identity. And then we say that an ideal P of R is a prime ideal if, whenever the product A times B is inside of P, then either A is in P or B is in P. Or, of course, they could both be inside of P. And now let's compare this to the definition of a prime number, or really like the equivalent definition of a prime number. So a number P in the natural numbers is prime if and only if, when P divides AB, we know that P divides A or P divides B. So inside natural numbers, this is generally not the definition given, but it can be proven to be equivalent to the definition. So here we've exchanged being an element of this ideal with divisibility. And that's really how you want to think about this notion of an ideal within a ring. It's like generalizing the notion of divisibility. And that's what we see here with this definition of a prime ideal versus a prime number. Okay, so for our next definition, let's take a proper ideal M of R. So let's recall that a proper ideal cannot be the entire ring. And this ideal is called maximal, or a maximal ideal, if whenever we have another ideal I that lives between M and R, then I must be equal to M or I is equal to R. So in other words, we can't fit any ideals between M and R. That's the maximality condition here. Okay, so now let's start with the following claim, which gives us even more motivation to this word prime inside of the definition of a prime ideal. So the prime ideals of the integers are either the trivial ideal, which just contains 0, and the ideal generated by a prime, pz. Or sometimes this is also written as the principal ideal generated by P. That's just two different notations. So this is nice because we know every ideal of Z is a principal ideal. It's generated by a single element, and we can take that element to be either 0 or a natural number. And what this is saying is that if we have a prime number, then we get a prime ideal. And likewise, if we have a prime ideal, then we get a prime number. So that's pretty cool. Okay, so let's look at each of these cases individually. So let's first look at the case where we have that trivial idea that just contains 0, and this is super easy. So let's suppose that A times B is inside of this trivial ideal, but there's only a single element in here and it's 0. So that means A times B is equal to 0. But then, since the integers is a integral domain, we know that that tells us that A is equal to 0 or B is equal to 0. But in turn, that tells us that A comes from the singleton 0 or B comes from this singleton containing 0. But starting here and ending here is exactly the condition to be a prime ideal. Okay, so now let's move on to the next case. Let's suppose that we've got a non-trivial ideal. So we've got this ideal, which I'll call P, which is inside of the integers, and it's a prime ideal. Okay, so last time we showed that every ideal of the integers is a principal ideal. In other words, it's generated by a single natural number. So we can have P is equal to NZ, or this principal ideal generated by N, for some N, which is a natural number. And this is where we come to this point that I left out here, and that is that we actually need P to be a proper ideal. So I'll put that P is not equal to R there. But that means that n is not allowed to be 1 here. So in other words, n must be bigger than or equal to 2. So there, we fixed that pretty easily. So we've got our prime ideal must be generated by a natural number which is bigger than or equal to 2. So now let's try and factor in. So let's write n as a times b, and let's pick a and b from the set between 1 and n. So we're trying to factor in, and then we'll see that we fail. Okay, so notice that we have a times b is equal to n, which is inside of p. Okay, so that's pretty clear. But since p is a prime ideal, that means that a is inside of p or b is inside of p. And now, without loss of generality, let's assume that a is inside of p, which is equal to n times z, which, let's recall, is equal to the set containing minus 2 times n, minus n, 0, n, 2 times n, and so on and so forth. That's this set n times z. Okay, but now let's look at what we have here. We have a is between 0 and n, and a is from this set. So there's only a single element between 0 and n that is in this set, and it's that right there. Or maybe likewise, we could put these two conditions together and say that a comes from the set nz intersected with the set 1 to n, which, like I said, is the singleton n. Okay, well, all in all, we get that a is equal to n, and thus b is equal to 1. So we tried to factor in, and we determined that the only factorization of n was as n times 1. But the numbers that only have that sort of factorization are exactly the prime numbers. So that means n is equal to p, a prime number. I'm just renaming n as p to make it look like a prime number. Okay, but now putting this together, we see that our ideal p is really equal to p times z. In other words, the principal ideal generated by p. But that's exactly where we wanted to end up. Now let's look at some examples of ideals within a ring that exhibit this maximality condition. So now I'd like to examine the diagram of ideals inside of Z24 and Z30. This gives us a nice description of the maximal ideals using this picture. Okay, so let's look over here. A maximal ideal is any proper ideal where you can't fit any other ideal between that maximal ideal and the entire ring. So by this visualization, it's pretty easy to see what the maximal ideals are. So the maximal ideals inside of Z24 are the principal ideals generated by 2 and 3. That's because there's no ideals between 2 and Z24 or 3 and Z24. And likewise, inside of Z30, there are 3 maximal ideals. So there's this one generated by 2, another one generated by 3, and finally another one generated by 5. And those are all of the maximal ideals inside of Z30. So now let's look at a concrete example of a maximal ideal in a larger ring. Next up, we'll show that the principal ideal generated by x squared plus 1 inside of the polynomial ring where the coefficients are real is in fact a maximal ideal. And in fact, using the result that we'll have on the next board, this is a lot easier than the proof that we will give. That being said, I think it's illustrative to see maybe this proof without that upcoming result. Okay, so let's maybe first suppose that we have an ideal I of R adjoin X such that we have I lives between x squared plus 1 and R adjoin X. Okay, nice. And then we're going to use a fairly standard strategy for showing things are maximal. And that is, we will assume that this is not equal to the smaller ideal x squared plus 1, and then show that it must in fact be equal to the larger ideal r adjoin x, or the larger ring r adjoin x. So since I is not equal to this, but this is contained in I, we can take some element from I which is not inside of the ideal generated by x squared plus 1. So let's call that p of x. So like I said, this is in I, but not in the ideal generated by x squared plus 1. And now we're going to essentially do polynomial long division on this polynomial. And we're going to divide by x squared plus 1. So let's write it like this. So now we're going to write p of x as the polynomial x squared plus 1 times q of x plus r of x, where that is our remainder. And in fact, I guess we're using something that we haven't quite gotten around to proving yet. But that being said, it's kind of well known. And this is like the polynomial long division, or maybe the Euclidean or the division algorithm for a polynomial ring. And so this division algorithm ensures that the degree of r of x is strictly less than the degree of what we divided by, but the degree of what we divided by is x squared plus 1, so that degree is 2. So that means the degree of r of x is less than or equal to 1, but likewise it's got to be bigger than or equal to 0, because everything has a degree bigger than or equal to 0. But what does that tell us? That tells us that we can write r of x as ax plus bx, with a and b in real numbers, but both not equal to 0. And how do we know that they're both not equal to 0? Well, if they were both 0, then we would have perfect divisibility here. But then p of x would be a multiple of x squared plus 1, but that means it would be inside of this ideal generated by x squared plus 1, which we assume that it is not. Okay, great. But now let's solve this equation for r of x, but we'll solve it in light of it being equal to ax plus b. So we have ax plus b is equal to p of x minus x squared plus 1 times q of x. And now let's notice where these things are. So this p of x is inside of I. That's by this assumption right here. And then next, this 1 plus x squared times q of x is inside of the ideal generated by x squared plus 1, which is a subset of I. That's by maybe this right here. But that means both of those are inside of I, which means this is most definitely inside of I. So we have ax plus b is inside of I. But from here, what we can do is use the fact that I is an ideal. So let's notice that we have some other things in I. So first of all, we have ax minus b times ax plus b. That's by just the definition of an ideal. Recall, if something is in the ideal, then any multiple of that something is also in the ideal. So this is equal to a squared x squared minus b squared. And like I said, that's inside of I. So what are some other things inside of I? Well, notice that x squared plus 1 is inside of I, which means if we multiply that by a squared, that's also going to be inside of I. So we have a squared x squared plus a squared is also inside of I. Okay, so what did we use here? Here we used the fact that ax plus b was inside of I. And here we use the fact that x squared plus 1 is inside of I. Okay, so now we have the following two elements inside of I. But since I is a subring, that means their difference is also inside of I. So let's take their difference and notice that that cancels this a squared x squared, leaving us with a squared plus b squared is an element of I. But let's also notice that a squared plus b squared is not equal to 0. And that's because a and b are both not 0. But that means that a squared and or b squared are both bigger than 0. Anyway, that cannot be equal to 0. But what does that tell us? That tells us that 1, which is equal to a squared plus b squared times 1 over a squared plus b squared is also inside of our ideal. Because look, it's a multiple of something inside of the ideal. And now that we've got 1 inside of the ideal, we in fact have everything inside of the ideal. We can see that very easily. Let's take f of x inside of R adjoin x, and notice that f of x is the same thing as f of x times 1. It's a multiple of something inside of the ideal, which means it's inside of the ideal. But that means that R of x is a subset of I, but I is already a subset of R of x. That must mean that they are equal. So we have I is equal to R adjoin x, which is exactly what we needed to show for this maximality condition. Okay, so anyway, we've got a maximal ideal of R adjoin x. Okay, so now I want to look at two very important results involving prime and maximal ideals. Okay, so the first of our big results starts with R being a commutative ring with 1 and P being an ideal of R. And then the result says that P is a prime ideal if and only if R mod P is an integral domain. So often it's easier to check if something is an integral domain than it is to check if something is a prime ideal. So this gives you a nice classification of prime ideals. Okay, so let's prove this forward direction first. So let's suppose that P is a prime ideal, and let's start the setup for testing if something is an integral domain. So we've got A plus P and B plus P are in R mod P such that we know that A plus P times B plus P is equal to 0 plus P. In other words, we've got things that may be zero divisors. But recall that something is an integral domain when there are no zero divisors. So we'd like to show that one of these must be 0. So in other words, the only way to take a product of two things and get 0 is for one of them to already be 0. Okay, so let's use this definition of multiplication within a quotient ring to rewrite this as A times B plus P must be equal to 0 plus P. But next up, we'll use the equality of coset theorem to say that this is the same thing as A times B is in P. But that's really good news because now we're ready to use the primeness of the ideal. That tells us that A is in P or B is in P. But now we can move this back into the quotient ring. So that means that A plus P is equal to 0 plus P. That's if A is in P. Or that tells us that the coset B plus P is equal to 0 plus P. That's if B is in P. But that's exactly what we needed. So let's review what we did. We took the product of two things within the quotient ring and we got 0. And we showed that one of them must itself be equal to 0 in the quotient ring. And along the way, we used as a tool that P was a prime ideal. Okay, so that proves this forward direction. Now let's move on to the reverse direction. Okay, so moving on to the reverse direction, let's start by supposing that R mod P is an integral domain. And then we'll begin our setup to show that P is a prime ideal. So let's also take A and B in R such that A times B is inside of P. And then of course we want to show that those satisfy the following condition, A is in P or B is in P. That's what it takes to have a prime ideal. But we need to move into the quotient ring because that's the tool that we have. We have R mod P as an integral domain. So how can we do that? Well, this condition that A times B is in P is exactly the condition for AB plus P to be the same coset as 0 plus P. But now we get to do some of the stuff that we just saw in the other direction in reverse. So let's factor this left-hand side to get A plus P times B plus P equals 0 plus P. That's by the definition of coset multiplication inside of the quotient ring. But now we'll use the fact that R mod P is an integral domain to tell us that A plus P is equal to 0 plus P or B plus P is equal to 0 plus P. Okay, great. But now we'll use the coset equality theorem to say that this means that A is in P or B is in P in each case. But let's see, that's exactly what we needed to do. We started here with A times B is in P, and we ended here with A is in P or B is in P. And along the way, right here in fact, we used the fact that the quotient ring was an integral domain. Okay, so that finishes this proof. And now we're going to look at a similar result regarding maximal ideals. Now this result starts with the same setup. We've got R as a commutative ring with 1, but now we have an ideal which we'll call M. And the result is that M is a maximal ideal if and only if R mod M is a field. Okay, so let's get to it. So this forward direction first. So let's suppose that M is a maximal ideal. And what we want to do is show that R mod M is a field. But to be a field, every non-zero element must have an inverse. So let's take a non-zero element within this quotient ring. So that'll be of the form A plus M inside of R mod M, and it needs to be non-zero. So the fact that it's non-zero means that A is not an element of M. Because if A was an element of M, this would be a zero element inside of R mod M. Okay, nice. And now we want to consider the following like small chain of ideals. So we've got this ideal M, and notice that this ideal M is strictly contained in but not equal to the sum of the principal ideal together with the ideal M, that principal ideal generated by A. So we talked about sums of ideals on the last video, so that's what we're applying here. So just to reiterate, here we have our maximal ideal, and the maximal ideal is a natural subset, or really sub-ideal, of the principal ideal generated by A plus itself. Okay, and then this itself is an ideal of R because we know the sum of any two ideals is an ideal. But now let's recall that M is a maximal ideal. That's our assumption here. But the definition of a maximal ideal says there's nothing in between M and R. Well, we already assumed that this thing is not equal to M, or we constructed it so that it's not equal to M. So that means it must be equal to the ring itself. So in other words, we have the ideal A plus M must be equal to the ring R. But notice the element 1 is inside of R because R is a commutative ring with 1. So that means in particular, the number 1 is in A plus M. Okay, but now we know the format of things inside of this. So that means that 1 is equal to A times R plus little m for R inside of, let's see, R, and little m inside of M. Oh, but now let's notice that that means we have the equality of the two cosets within R mod M. And that's by that coset equality theorem that we use over and over and over again. we have the coset AR plus capital M is equal to the coset 1 plus capital M. That's because the difference of these two elements is equal to lowercase m, which is an element of M. Oh, but now we can factor this left-hand side using the definition of multiplication in the quotient ring. We have a plus m times r plus m is equal to 1 plus m. But look at it, we just found the inverse of a plus m. That's because this is the identity with respect to multiplication inside of the quotient ring. So we have a plus m inverse is equal to r plus m. Okay, so let's see what we've done. We started with a maximal ideal. We took a non-zero element in the quotient ring and we found an inverse, a multiplicative inverse for that non-zero element. But that's exactly the definition of a field. Every non-zero element has a multiplicative inverse, so that means that R mod M is a field in this case. Now, let's look at the reverse direction. Okay, so starting with the reverse direction, we'd like to suppose that R mod M is a field. And then next, let's take an ideal that is between R and M based off of this. So let's do that. And like I said, I, which is an ideal of R, is such that it lives between R and M. And now, like, without loss of generality, we may as well assume that it's not one of them and then show that it's the other. So let's maybe make the assumption that it's not equal to M, and thus we'd like to show, so let's point that out over here, we want to show that I is equal to R. Okay, great. And again, in this case, we have to use the fact that R mod M is a field to get there. Okay, so let's take something which I'll call A inside of I, but outside of M. But notice that means that A plus M is non-zero in the quotient ring R mod M. So like I said, it's non-zero. Now, non-zero elements in R mod M are invertible because R mod M is a field. So let's find the inverse. So let's take B plus M inside of R mod M such that, well, it's the inverse of A plus M. So in other words, we have A plus M times B plus M is equal to 1 plus M. But let's notice that that means that A times B plus M is equal to 1 plus M. Oh, but then by coset equality, that means that A times B minus 1 is an element of M. But then by our assumption, that is a subset of I. So that means that A times B minus 1 is an element of I. Okay, but let's look at this. A is an element of I from our assumption right here. But that means that A times B is also an element of I. But if A times B is an element of I, and A times B minus 1 is also an element of I, that leads us to see that that means that 1 is also an element of I. But now if 1 is an element of I, then that means that everything is an element of I, and we can see that easily. So let's take a little r inside of the ring, and notice that little r is equal to little r times 1, which is inside of I, which tells us that the whole ring is a subset of I. But we assumed that I was a subset of R, so that shows that they are indeed the same. So we have I is equal to R. Okay, so let's review what we did. We took an ideal between M and R. It was not equal to M. And then, using the fact that R mod M was a field, we showed that this ideal had to be equal to R, showing that there are no ideals between M and R, which is exactly the condition for an ideal to be called maximal. Okay, so now let's look at some other examples. Now let's look at some quick examples. So let's look at the principal ideal generated by X inside of the polynomial ring Z adjoin X. Let's notice that this is a prime ideal because z adjoin x mod x is isomorphic to the integers, and the integers are an integral domain. But this is not a maximal ideal because the integers is not a field. So this gives us an important example of a prime ideal which is not a maximal ideal. So whenever you introduce notions like this, you'd always like to check if there are examples of one which is not another. Because let's notice very, very quickly that all maximal ideals are prime ideals. That's essentially because all fields are integral domains by our last theorem. So it's an important exercise to show that you've got prime ideals that are not maximal, and here's an example of one of them. And now let's look at another example where we have an ideal which is not prime inside of the Gaussian integers. Let's look at the principal ideal generated by 3 minus I. So I'll call that capital I. And like I said, that's in z adjoin I, the Gaussian integers. And now let's notice that if we take the coset 1 plus I plus capital I and 1 minus 2I plus capital I, you get 3 minus I plus capital I, but 3 minus I is most definitely an element of I, given that it generates I. So that's the same thing as the coset 0 plus I. That makes these two things zero divisors. But since there's zero divisors, that means we do not have an integral domain. But since we do not have an integral domain, this is not a prime ideal. Okay, so now let's look at some more examples of ideals. Now we're going to look at two more examples of creating new ideals from not just old ideals, but old objects. So let's suppose that we've got a commutative ring now. It doesn't necessarily have to have a multiplicative identity. Then given any subset A of the ring, the annihilator of A, written as an A, is all of the elements of R that multiply into all of the elements of A and give us 0. So in other words, they annihilate all of the elements of A. Okay, so next up, we want to look at something called the nil radical of an ideal. So given any ideal of R, the nil radical of I, which is denoted by this like square root symbol of I, but we read that as nil radical, that's all elements of the ring, so that some power of them is in the ideal. So in other words, for some natural number n, r to the n is inside of the ideal. And then there's a special case of this when we look at the nil radical of the trivial ideal. In other words, the nil radical of the ideal with just 0. So those are the set of all the nilpotents, sometimes called n sub r. And that's going to be everything that has some power which is equal to 0. Okay, so let's look at some examples. So let's say that we're inside of Z12 and we want to look at all of the nilpotents inside of Z12. So that's going to be everything so that when you take some power of it, you get 0 inside of Z12. So in other words, you get a multiple of 12. Well, you can see that inside of Z12, that's simply going to be 0 and 6, which is the principal ideal generated by 6. And similarly, inside of the integers, the nil radical of the principal ideal generated by 12, so that's going to be every integer, so that when you raise it to some power, you get a multiple of 12. Well, that's just going to be every multiple of 6. In other words, the principal ideal generated by 6. And we can sketch this out pretty easily. So if a to the n is equal to a multiple of 12, so in other words, it equals 12 times k, then we know that 2 divides a to the n and 3 divides a to the n. But that tells us that 2 divides a and 3 divides a. But if 2 divides a and 3 divides a, that tells us that 6 divides a. In other words, that tells us that A is in the principal ideal generated by 6. Now let's notice that 6 squared is equal to 36, which is a multiple of 12. So technically this just shows one of the containments in this direction, but it's pretty easy to show the other containment as well. And now we can do this in general pretty easily. So let's suppose we've got a prime factorization of n as p1 to the r1 times up to pk to the rk, and those are distinct primes. Then it turns out that the nil radical of the principal ideal generated by n is simply equal to the principal ideal generated by the product of those prime factors without the exponents. And the proof follows essentially the same way as this proof goes. So this corresponds to the idea of the radical of a number in number theory, which is simply the product of all of the primes that divide that number without those exponents. Okay, so let's see an example over here. The nil radical of the ideal generated by 360 is simply the ideal generated by 15. That's because 360 is equal to 2 cubed times 3 squared times 5. But that means the primes that we have are 2, 3, and 5, and their product is 30, not 15. I was wrong there. I had a typo. So it's 30. Okay, so now let's prove that these are in fact ideals, and then we'll prove some other associated results. Okay, so now let's prove that the annihilator and the nil radical are ideals, starting with the annihilator. So let's first show that it is a subring, which, recall by the subring test, it must be closed under subtraction and multiplication, and then we'll prove the absorption property that we need for ideals. Okay, so let's suppose, like I said, that R and S are elements of the annihilator of A. And then what we want to show is that their difference is in the annihilator of A, and their product is in the annihilator of A. But let's see what the phi is to be inside of the annihilator of A. You must multiply into any A and get 0. Okay, so let's also suppose that A is in A, because that'll be an important tool. Okay, so now let's notice that R minus S times A is the same thing as R times A minus S times A, but that's equal to 0 minus 0, which is equal to 0. That's because R and S are both in the annihilator. Oh, but that means that R minus S is in the annihilator as well, because it satisfies this rule that if we multiply it into any element of A, we get 0. Okay, so now let's show that their product is also in the annihilator, and this should be fairly straightforward. RS times A by associativity is R times SA, which is R times 0, which is 0. But that's exactly the condition we need for R times S to be in the annihilator of A. So that means it is a subring. So now let's prove this absorption property. So let's suppose that we've got a new element. Let's maybe call that new element B from the ring. And then we need R times B to be in the annihilator of A. That's the absorption property of ideals. And let's do that by looking at R times B times A. Okay, but then by associativity and commutativity, we're in a commutative ring after all. That's going to be equal to B times RA. But since R is in the annihilator, that's equal to B times 0, but that's equal to 0. So the fact that R times B times A equals 0 means R times B is, in fact, in the annihilator of A. So we've got this absorption property. Anything in the annihilator times anything in the ring is in the annihilator. So that means the annihilator is an ideal. Now let's show that the nil radical is an ideal. So now let's show that the nil radical is an ideal, starting by showing that it is, in fact, a subring. And we'll do this by showing it's closed under subtraction and multiplication, just like before. So let's suppose that we have A and, or maybe we'll call it R and S inside of this nil radical. But notice that means that R to the M is inside of I and S to the N is inside of I for some M and N inside of natural numbers. So it's not for all, it's for some. Okay, good. But now we'll do this trick with binomial expansion. So let's look at R minus S to the M times N. And expanding this out, that's going to give us the sum as, let's see, k goes from 0 up to m times n of the binomial coefficient mn choose k. And then also a -1 to the k because we've got this minus sign right here. And then we'll have r to the mn minus k and then s to the k. And now let's notice by this construction, regardless of where we are in this sum, either this exponent right here will be bigger than or equal to the maximum of mn, or this exponent right here will be bigger than or equal to the maximum of mn. The important thing that is that at some point or at all points, one of them is bigger than or equal to the maximum of mn. But that means that one of these is always inside of the ideal. But by the absorption property of the ideal, that means the product is always inside of the ideal. But then by the closure of a sum or a difference under an ideal, that means this whole thing is always inside of the ideal. But if this to this exponent is inside of the ideal, that means that r minus s is inside of the nil radical of this ideal as needed. Okay, so now let's move on to the product, and this is like essentially the same sort of idea. Let's take r times s to the m times n, and notice that that gives us r to the m to the power n, and then s to the n to the power m. But notice that each of these is inside of I. So this is a little bit overkill, but I think that's okay. This is inside of I and this is inside of I, which means they're both, or their product is inside of I. But this to the mn being inside of I means that r times s is inside of the nil radical of I. Now let's prove this absorption property. So let's take A from the ring, and we want to show that A times R is inside of this nil radical. Okay, but we can do this pretty easily. Notice that A times R to the m power is A to the m times R to the n. But now we know that times R to the m, but now we know that R to the m is inside of I. But then by the absorption property of the ideal, we know that A to the m times something from I is an element of I. But that's exactly what it takes for AR to be in the nil radical. So that means, in fact, that A times R is in this nil radical of I, meaning that we have the absorption property, and thus this nil radical is an ideal. Okay, so there's this proposition that goes along with these nil radicals of ideals that I'll state but not prove. A proof will be either in class if you're taking my class or in an example video which is forthcoming. So if I and j are ideals, then the nil radical of the nil radical of I is the same thing as the nil radical of I. So this nesting doesn't really do anything. And then the nil radical of I intersect j is the intersection of the nil radicals. So these are fairly straightforward. And these will be exercises in class. Okay, then here's some nice warm-ups. So let's consider the ideal, which is 2z inside of z. Let's show that's maximal, but the ideal I adjoin x is not maximal in the polynomial ring z adjoin x. And then, is it a prime ideal? Next, let's find all maximal ideals of the ring Z12 cross Z15. And finally, find the annihilator of the singleton 15 inside of Z36. And that's a good place to stop.